Hello, community! Today we have a look at a new idea by Stanford University and OpenAI. And this is the publication we're going to talk about. Stanford University, Microsoft Research, and OpenAI came together to publish something about a recursively self-improving code generation. And you might say, hey, that sounds interesting. Yes, absolutely. Now, let's make sure we're just focusing here on self-improving code, so on a very limited array. And we talk about a method in which code that applies here an LLM to improve some arbitrary solution is simply applied recursively to improve itself within a defined scope. And you might say, is this in any way interesting for us? Well, let's start at the beginning. And we have a little generic LLM, like OpenAI's O1 model, for example. And then we know that, let's say Apple does this, we have adapters that we put on top of this generic LLM. And those are very specific adapters, let's say for photos, or for your iPhone, or for the music that you play, or for videos. So you have a generic LLM and very specific adapters for your specific task. And the beauty, this is so cost effective and fast to run on edge devices because your generic LLM stays the same for all the different tasks. And for each task, you only fine tune here your specific adapter. And you can think of these adapters as a plug and play model that adapt the LLM to specific use cases. Great. Since only the adapters are fine-tuned, you use LoRa. It is fast, it is great, it is beautiful. But this is state-of-the-art. So if we have now a lot of tasks coming in, user queries, specific user queries, we have data from the environment and we have access to tools, or maybe tools request some action from us, from our AI, what is the new idea by Stanford and OpenAI? Well, it is easy. We just have something like a scaffolding logic controller. We just have here a protective shield in front of our LLM that does something that has kind of an intelligence. Let's have a look at this. Now, the beauty is that our generic LLM codes this controller. This is a freely programming code object that you can define according to your specific task. And then, of course, you can train it for a complexity level 3 out of 10. Or maybe, if it's a challenging task, you go for a complexity level 5 out of 10. Because this logic controller, if it has some predefined intelligence by our LLM, it must understand the complexity of the task. Because if a task comes with a complexity level 4, so we know which data to use and which tools to use, but the logic controller would only be able to go up to a complexity level 3 if it will fail. So you have to have your logic controller, your shield out there to be intelligent. Great. So yeah, it should be self-learning, come on. And it should be able to reconfigure itself. Hey, we're in the age of AI, so no problem here. So what we have now is here a scaffolding logic object, a code object if you want, as a separate object to indirectly enhance now the performance of our generic LLM on specific tasks. Why? Because imagine whatever comes in, the logic controllers does something to the data, and then the real input here to our generic LLM is pre-selected, has already here been pre-processed by a kind of a logic. The data and the task and everything has been already prepared in the optimal way for our LLM. Easy. It defines the steps. This logic controller defines the strategies and the mechanisms which the LLM here is queried. So whatever the LLM has been particularly pre-trained on, so whatever the LLM is particularly good at, this shield here makes sure that all the data that come in are prepared in the special way like the LLM likes it. Isn't this beautiful? So, one of the tasks it can do, it can break down a high complexity task into smaller, lower complexity subtasks. Iteratively, and this is now the self-learning aspect, this thing here has kind of an intelligence, so it can learn and take time, it can improve the solution itself. And this is the interesting part, we will incorporate now techniques like a beam search or a genetic algorithm or more complex strategy that this thing becomes a self-learning object. And here the beauty comes in. Now it gets interesting. So, very easy for my green grasshoppers. This scaffolding logic that we put now as an intelligence shield, no, Stanford OpenAI and Microsoft published this as a shield in front here of our generic LLM. And this shield here determines how to use here the LLM abilities to the best in the available energy and the available time on your edge device, on your iPhone, or maybe on your iWatch or wherever you are. Nice. Yeah, and officially we call this a recursively self-improving code object. Okay, I call it an intelligence shield. Now, understanding now, please, that this shield is created by the LLM for a particular set of tasks. So this is programmed by the LLM. This is kind of the intelligence, and it uses here the intelligence of the LLM. And since it is freely programmable, we can now implement some code that can, if you want, self-learn, self-improve over time. Now, you know what we have today. Today we have a simple prompt, and we do all the prompt engineering here. This is the input pipeline here to our generic LLM. And you see already that the big global corporations, they have prompt optimizer and whatever. We have DSPy, you know, this old stuff from yesterday. We try to optimize here this input channel to our LLM to make it here the best possible configuration in text, in data, in video data, audio data, so that the LLM is immediately able to improve on it. Let's have a look here, for example, at OpenAI. Here you have the HTTPS link, and they have now this, they explain here how OpenAI is doing here the prompt generation. And they say, if you press here the generate button here in the playground of OpenAI, lets you generate here prompts. We, as OpenAI, we generate the function that you need and the schemas just from the description of your task. So you, as a user, you are not tasked anymore to write the perfect prompt or to find the correct function calling, or to have here a structured input-output schema. This is now all done, what a coincidence here, by those corporations. So they provide here the best input to their LLMs. And they say creating now these prompts and these schemas from scratch can be time consuming for you as a user. So generating them for you can help you to start quickly. So our generate button uses now two main approaches, prompts. OpenAI tells us we use meta prompts that incorporate the best practice we know as OpenAI to generate or improve the prompts that you use on our machines, on our infrastructure for our O1 model. And also for the schemas, meta schemas, yeah, we have JSON and function syntax, of course. And they say, hey, currently we use the meta prompts, but we looking forward here, DSP and gradient descent, to new methodologies. And you know what? Those methodologies we can further develop to self-learn. What a coincidence, eh? And they specify, going further, a meta prompt instructs the model to create a good prompt based on your task description or improve an existing one. So all that we used to do as a user, as a human, we humans had to do prompt engineering. Now those times are gone, finally. You just talk to your AI by OpenAI and you say, hey, I have this particular task. So now you stupid machine, create the perfect prompt, create the perfect function that I need, create all the tools that I need, make them available for me. And you as a machine, you define here the perfect JSON format, you integrate here the graph-based data. I don't want to take care about it. I'm human. You machine, you optimize yourself. You see, easy. So if OpenAI is going now here from a non-profit to the real profit-oriented, you know what products will come out and what products will amaze future users. But we are here for science, so we want to understand how they do this. And here we have now the meta prompt by OpenAI. And you see we have here quite some interesting things, and then we just have here more or less the format structures. But let's go here where the intelligence is, and this is in green. Let's have a closer look. So this is the green one, and let's have a look that we can read it. So part one of the green one. Now, The OpenAI system is now tasked here to understand the user task, grasp the main objective, the main goals, the main requirement, the main constraints, and what the user expects as an output from us, because we are just a simple AI machine. And they say, hey, if an existing user prompt is provided, improve it only if it is simple. You know, the simple humans with their simple prompts. For more complex prompts, enhance now the clarity of the user prompt and add all the missing elements that we as OpenAI need for our structure, for our platform. And now comes something interesting. Reasoning before conclusion. Encourage reasoning steps, and I will show you we already implemented this in another video of mine, before any conclusions are reached. The reasoning order is important, we know this, and conclusion, classification, or results should always appear last in the prompt structure. Examples include high-quality example, if helpful, using placeholder in brackets for complex elements. And you see, they have now this meta prompt to optimize the human prompt. And they go on for clarity, consciousness, clear, specific language, the formatting is used, preserve here the user content. This would be nice, no? So they tell you, hey, if the input task of the prompt includes extensive guidelines or examples, preserve them entirely, because maybe this is already a machine-optimized prompt from another AI system, or as closely as possible. However, if they are vague, considering break down this thing into substeps. Reduce the complexity from a C8 of 10 level to a C2 out of 10 and have multiple steps. Keep the details, keep the guidelines, the examples. Constant do include constants in the prompt as they are not susceptible to prompt injection. Output format, task outputting well-defined structured, like JSON whatever, toward outputting as a JSON file. JSON should never be wrapped in the code blocks unless explicitly requested, and then you have all the output formats. So you see what they're already trying to do. You don't need the perfect prompt anymore as a user. The system will create its own perfect prompt. It is like here, this is already an intelligence shield before the original OpenAI LLM, optimizing already the data input in the data pipeline to the LLM. And this is exactly why I waited here 8 weeks to show you this particular publication by OpenAI in Stanford. And you know, we had here in this prompt optimization now on a different level, on a kind of automatic differentiation via text. I had this video, I think 2 months ago, where I showed you the DSPy, the self-improving machine learning system here for an advanced prompt optimization, which was done, by the way, by Stanford. And you say, what a coincidence. DSPy now has 1 year later a much more powerful system, and this is called TextGrad. This is an automatic differentiation via text. And also this was discovered by Stanford University. And you say, what a coincidence, no? So we have now from the historic, if you want, evolution of those prompt engineering systems here, this intelligent shield layer before we have here our original LLM, there are already a lot of things happening. And now, it seems to me, now we have some consolidation. Because this study here, 8 weeks ago, from Stanford University, Microsoft, and OpenAI, is exactly focusing here on this particular intelligence shield. They do not go for the general prompt structure. They picked out a little tiny segment of code generation, but they build it in a way that you immediately understand what they are heading for in their next development stages. Great. So we understand now there's a lot of things going on here in front of the LLM, the intelligence shield, what I call it. OpenAI tells us now here, what a coincidence, 8 weeks later after their cooperation here with Stanford University, that, as I showed you, they will integrate a little bit later more advanced techniques like DSPy, this is exactly what we did here, and gradient descent, but you know the real powerful, the workhorse is TextGrad. And I already implemented this about 6 weeks ago, and it is running now for 4 weeks. And it needs time to learn those systems. This intelligence self-learning shield, you can't just start it and wait hours. it needs weeks to optimize in a background process, but more about this later. So here we have it now, this idea, this new idea. This intelligence shield, it has a prompt optimization here, particular for some proprietary LLMs only on their platforms. And this protective shield, and why you might say, why you call it shield? Well, you could add here a cybersecurity element, no? A self-learning cybersecurity defense agent. But this is not part of the original study as published by Stanford and OpenAI. So this is just my idea, what I implemented. So we have LLM creates here a protective shield. It codes a protective shield, an intelligent self-learning shield that the LLM can further program. The more intelligent the shield must become given the complexity of the task of the queries and the complexity of the tool use. Beautiful. So if you ask me, this shield, where does the intelligence come from? It is the intelligence of the LLM. And they in the study say, if you take here a little generic LLM, it will not have the logical reasoning capacity to do this programming. Because this will be a recursively self-improving code object. You really, what a coincidence, have to go with the big boys here, with these huge LLMs from Microsoft, or yeah, more or less it is OpenAI. So you understand where the money is located. Great. There is also an interesting part, Just yesterday, OpenAI published here this swarm. This is only an experimental framework here, but they go here with a multi-agent orchestration. And I looked at this and immediately had an idea, because look, this is here an LLM with an intelligence shield. And if you want, all of this here creates one agent. Now imagine you have multiple agents, and in each of those multiple agents, you have a specific LLM plus its own shield. This is now an interesting part, how this LLM, knowing that it is part of a bigger set of agents, is there a feedback mechanism from the other swarm elements? But this would be beyond today's video. This will be a later video. About, multiple weeks ago, I did this video on a self-correcting LLM. So you might say, hey, wait a minute. We have a shield in front of the LLM that is now doing all the prompt optimization, cybersecurity logic. It breaks down complexity task into simpler tasks. It is doing all the preparation work that we have an optimal data structure and data inflow to our LLM, so that the LLM is pre-trained on particular this complexity level and able to solve all the tasks that come through. And if this shield is self-learning, what if we do a self-learning or a self-correct LLM? Let's show it in this video. And this was an idea by Google. And I showed you exactly how an LLM can self-correct itself. And the step from a self-correcting LLM to a self-learning LLM, yes, you guessed it. So this brings us now to my last video from yesterday, where I was talking here about Gödels AI Agent, a purely recursive self-improving AI. So this AI is now complete. So we have a self-improving intelligence shield. This is what we have in this publication by Stanford and OpenAI, and a self-improving LLM. Please note that in this current publication, the self-improving LLM has not been published yet by Stanford and OpenAI. So, but you understand where we are heading for. If you have not seen my last video, I was talking about Gödels agent, about an LLM, about a particular policy, about the memory, the utility function, the self-referential code, all the decision function that we need and the interaction with the environment. And I showed you how those elements work together in Gödels AI agent to have a real recursive self-improving AI. This means we not only have now the self-improving and self-learning shield, like we have today in this video, but with Gödels agent, you would also have a self-learning LLM, as I've showed you in another video. But yeah, I think this is what OpenAI is waiting for their for-profit entry in the market. And you might say, okay, let's have a look at this intelligence shield. Show me, since it's a code object, show me the inner working of the intelligence shield. And here from the publication, this is it. This is the complete code here. We have to start somewhere. So this is level 0. This is the beginning of our self-improvement. And OpenAI and Stanford said, hey, this is the code that we use. So you have an improve algorithm. And if you look at this, you have 3 inputs. You have an initial solution. Yeah, the task is to optimize a function, a mathematical function. This is the simplest idea. We start at the basic level. So we have to have a Python code solution that can optimize this mathematical function. Then we have to have a utility function. A utility function is simply that it scores the quality of the answer. And it says, hey, this was a good answer. This did not work at all. And let's say we rank it here, or we score it from 0 to 10. And then, of course, in our agent, we have to have an LLM. So you see, easy. We have the initial solution, we have the utility function, and we have an LLM. And this defines already our improvement algorithm. So here we have now the message for the system. I say, improve the following solution. And now I provide here a simple mathematical coded solution to optimize a mathematical function. And then I tell the system, hey, you as an AI, you will be evaluated based on this scoring function. So I tell him, hey, I use a particular utility function. I don't know, I go for the F1 score, I go for a particular benchmark parameter, I go for a generic level of accuracy. Whatever you need for your specific task, you put in here a utility function that is specific to your task and brings you the best results. We now say to the AI, hey, you as an AI, return us improved code solutions. And we tell the AI, hey, you are creative as you can, and your primary improvement must be novel and non-trivial. First, propose an idea and then do the code implementation. And you might say, but hey, I have Cursor. I have this thing here from Microsoft, with the plus, who is doing all the code engineering for us. Yeah, but we go a step further because we say, okay, beautiful. The LLM starts now, and let's say this is here O1 or GPT-4 Omni. The LLM creates now new code solutions, executable code, Python code, for example. But it creates multiple things. It creates 10 solutions. And then we run those 10 solutions, and the utility function here gives us back a benchmark data. And then the LLM, seeing this, understanding this, integrates now into this intelligence shield a utility function for the complete shield. And now we say, okay, now the best solution is simply take only the one that has the best result, which is not a good idea, but whatever. So it takes here, now again, initial solution and a utility function, as I showed you. Then the AI generates here multiple improved solutions, but here the AI coding here the shield. We are talking here inside the shield using a language model based on the prompt specific to the task and the evaluation criteria. And then from all the 10 solutions, it filters out and selects here the best solution in the shield using the utility function, yes. And then it returns only one, the best solution to the LLM in the input pipeline. So you see, all the prompt engineering, code optimization stuff is only, I say, 50, 60, 70% done before the data even enters the generic LLM. Officially here, OpenAI called this methodology not an intelligence shield, but this is what they call here a seed improver. So our seed improvement program, they say, simply prompts an LLM to generate here candidate improvement to an initial solution to a specific task and returns here the best solution given here a specific utility function. But now we went through this and you see, great. But you know what? Maybe the best solution is not what we are looking for. And they have now this self-taught optimizer. And this is now a method in which code that applies here a large language model to improve here some arbitrary mathematical solutions is applied recursively to improve itself with a defined scope. Hey, we're entering here the area of a self-learning code improvement. The approach begins here with a seed improver scaffolding program. This is our shield that uses here the LLM to improve a solution to some downstream task, as I just showed you. Then, as the system iterates and learns, the language model refines now its improver. This means, in my image, the LLM says now, hey, you shield, I see that you produce here solutions that are not perfect. I will recode you, the shield, to have here a little bit more intelligence, to use better algorithms that are more adapted to the specific task. So the LLM starts now to override the code of the shield, of the improver, and we have here a cycle going on between the LLM and its external shield. Then you, of course, you quantify the performance, you have an evaluation, you have the utility function, and you see this is now the cycle where the self-learning starts. Yeah, and they say here this optimizer shows that an LLM can act as their own meta-optimizer because, yes, of course, the shield is part of the intelligence of the LLM because it is programmed by the LLM here. So therefore, you can argue that this shield, also the code object, is a little bit outside of the original LLM. Of course, it is the intelligence sphere of the LLM. So you can say we have now meta-optimizers for the LLM, which is not really a precise formulation. And we have here that Stanford says, hey, we refer to this whole process as a recursively self-improving code generation, as they do this not on the complete textual prompt, but only on the code optimization. And they say, hey, which is inspired by, but they understand it is not a pure recursively self-improving RSI system, as the underlying LLM remains unchanged. So, of course, they didn't want to publish here the next step, that you don't make only the shield self-learnable, but also the LLM. And I showed you, we already have a video available on this channel, how to optimize the LLM also. So there we have it, no? We have a generic LLM, and this is beautiful, and we have, like Apple has it now, the different adapters if you want to do something with your photos, or if you want to do something with your music, or if you want to optimize your videos that you take on your iPhone, great. And you have just one generic LLM. And now we have this logic controller, this intelligence shield, this, as it's officially called, a recursively self-improving code generation object here in front of our generic LLM. And the LLM codes here continuously. This controller updates the code continuously depending here on the quality of the data that are provided now from the controller to the LLM. And this is now a cycle that goes on. And let's say the generic LLM has a complexity level of 7 and the logic controller starts with 1 out of 10. And you see, with the learning, the controller becomes more intelligent, and you understand exactly what's happening. Now, why is this so beautiful like Microsoft? Microsoft likes this, or then the profit-oriented OpenAI company likes this, because you have to do nothing to the generic LLM. You do not have to fine-tune this LLM. This is cost-effective. So this generic LLM remains unchanged. There are no extra costs. Why? For the specific task, we just put here our adapters on top of this generic LLM, and we have the performance. And for all the prompt engineering and code optimization and everything that runs, if you want, here at this intelligence shield in front of your LLM, since the LLM programs this, we only have to optimize this tiny little intelligence shield and not the huge LLM like the ChatGPT or the O1 or the, I don't know, Claude object or anything else by Google, like the huge Gemini that runs for a month in the pre-training phase on, I don't know, 10,000 GPUs. No, we only have to optimize the code for this element here, or maybe this elements here. This is so much cost effective for OpenAI or Google or Microsoft or whatever. And you see, this is nice. Of course, for you as a user, the price point is a completely different object. Yeah? But it's nice because this logic, this architecture allows here only this tiny object to be fine-tuned, and this can be done within a very short amount of time. Great. Now we understand here why Microsoft says, hey, I like this idea. Okay. Yeah, they say, hey, the original idea goes back here to Irving John Good. And this is a publication here from 1966. So if you're a little bit into philosophy and self and super intelligence or an ultra intelligent machine, you have here the first philosophical reflection in 1966 on this topic. Or if you watched my last video, which I highly recommend for any subscriber of this channel, I already talked about here the Gödel machines. And we have to mention Gödel machine from 2003, of course, here, as they give us here the blueprint for self-learning machines. And they say now, hey, this is our contribution. Formulating an approach to meta-optimization where a scaffolding system recursively improves itself. This is our shield. B, providing a case study where a system, the complete agent, using a modern GPT-4, can successfully recursively improve itself. And now we understand. If the system improves itself, it means that only the intelligence shield improves itself, and Microsoft does not have to touch here the tensor structure of GPT-4 or the internal workings of O1. And C, investigating here self-improvement techniques to implement it, including how the model circumvents safety measures like a sandbox. And I implemented here the exact opposite. I put here my cybersecurity measures, my self-learning cybersecurity defense algorithm into this intelligent shield. Great. So if you look now at one agent, at the core of each agent, we have an LLM or some rule-based instructions. And now the agent structure, the internal agent, would change, because now with this new idea by Stanford, Microsoft and OpenAI, you would have here a scaffolding code object in front of your generic LLM. That is now scaffolding, so this means it will continuously improve as coded by the LLM, and given the complexity of the incoming task here, it will adjust automatically without any human inputs. And as I told you, imagine we have a multi-agent system and we have multi-scaffolding objects that are not only code objects, but also prompt engineering and everything, and the complete complexity of the task analyzing and the cybersecurity elements in there. This now becomes a really multi-complex, multi-code object, multi-scaffolding problem, but more about this in a later video. Stanford tells us here, we looked now at this self-improvement. And we found that this, and they used here a GPT-4, so September 2021. I wonder why OpenAI is using here one of its oldest models. Okay, we understand. OpenAI is preparing here for a new product launch when it will be for profit. So, okay. But even the old GPT-4 version, So what they found, what does the system found as a self-improvement strategies? Beam search as the first one, we have a look at this. Genetic algorithms, decomposing, we already did this, and simulated annealing. Beautiful. So let's have a look now at inside the shield, and let's have a look at this, what they found. First element is beam search. Beam search is a heuristic search algorithm that operates by exploring a set of candidate solutions, keeping only the most promising ones and expanding them in each subsequent iteration. This means beam search narrows down here the search space by focusing here on the top K candidates, top 10 candidates, top 20 candidates at each generation, thus making a process more efficient. Now, an alternative would be a simply greedy approach. This means selecting only the single best solution at each step, but this can lead to local optima minima, where the system gets stuck here in a suboptimal solution without the power of having to escape from this gravity wall. So therefore, if the system autonomously finds beam search, how nice. So, beam search, if you're green grasshopper, avoids this by keeping multiple potential solutions here, the wide of the beam here, the top 10, for example, candidates, allowing the system to explore different paths and avoiding here a premature convergence to a suboptimal solution. If you want to see how beam search works here for my green grasshoppers, here a short summary for you. Now let's have it code. I'll give here a particular code example, Stanford. And I say, hey, this is a simple beam search algorithm that we start. And then you see how the system, how this intelligent shield programmed itself with new algorithm, found more sophisticated beam search algorithm. So now we have a look, how intelligent is this shield? What is it doing to the code base? I want to have a real practical example. We will see if it will leverage here the multi-threading, it will cache here the utility and the decays the temperature over time. So all ideas that we know from coding, but now the system codes here better solution. And here you have the code. I record this in 4K, so you can read this on your screen, no problem at all. Here we have the simple solution, and then you see here in this code, it just adds more complexity, more ideas. The code is improved significantly. Or if you want to have here an epsilon greedy strategy to balance the exploiting good solution and exploring new ones, this is another code example that they also published, and I played around with their code already weeks ago, and it's really working. This is amazing within a quite short period of time. And you might say, yeah, but listen, we have Cursor or we have other code LLM machines. So we don't have to go here from the level 1 to the level 3. And you're absolutely right. But imagine we do not start at the level 1. Imagine with this code, we start at the final level of Cursor, and then we ask the system, and now you optimize the latest Cursor complexity code system, and the machine self-learns here better code solutions. So you see, you have to see this also sometimes in perspective. Now, you know a better meta-heuristic is of course simulated annealing. So inside the intelligence shield, we now apply a better solution, a better meta-heuristic, simulated annealing as a scaffolding strategy for our self-optimization. The system, in this case an LLM-based scaffolding like here the STOP framework from Stanford, uses the concept of gradually reducing the randomness or the search exploration during the iterative process of solution refinement. If you don't know simulated annealing, how it works here in this self-optimizing system, there are some simple points. You have to start with an initial solution. Let's say this is a code generated by GPT-4 or whatever you have as a code LLM. And this is the starting point. And we have a starting temperature. And yeah, we'll have a temperature, of course, that is a more explorative solution. And then we explore a simple neighboring solution, perturbation to this code. So at each iteration, the system generates new candidate solutions by making small changes, or what we call perturbations, to the current code solution. And these changes, they take time. But sometimes they result in worse solution. This is a lower utility score, but they are considered part of the exploration process because we want to break free here of this gravity wall. We want to go to other areas to maybe want to find here a local minima or a local maximum here on our hyperplane. So we want to avoid here the local optima. Then see here, we accept here the suboptimal solution. We know this, here we are in the process. And unlike a greedy approach that only accepts here better solution, simulated annealing here allows the system to occasionally accept worse solution based on a probability function. And this probability function is controlled by a parameter called the temperature. And this is why it's called annealing, because it is for material science. And you know all of this. So at the start, with a high temperature, the system is more likely to accept worse solution, but enabling it to explore a wide range of potential improvement, searching the search space here with huge steps escaping from local maxima, and as the system iterates and cools down with a lower temperature rating, it becomes more selective, more precise, favoring here on improvements and refining towards a better code solution. This is the process of simulated annealing for my green grasshoppers. The last step here is now the cooling. And if the temperature parameter is gradually reduced over time, which means the system moves from an exploratory phase, accepting here also bad solution, quotation mark, to a refinement phase where primarily accept here the best solution. And this cooling process helps the system escape here all the local optima early on and settle into a more optimal global solution as the process goes on. And then either you have a stop criterion that you establish or you go for a fixed number of iterations, however, you have a time constraint, however, you define here a stop of the system. Now, of course, this is interesting. And if you read this study, please, I would recommend, this is a real beautiful publication here, Stanford, Microsoft, OpenAI. What they did not show us, what they did not mention, because they only looked here at a particular narrow slice of code. I was talking here in this video about Inside Strawberry's logic engine. And you know that OpenAI is a little bit careful, says, hey, you are not allowed to look under the hood how O1 systems are thinking. And in the video I showed you, hey, there is a simple solution, there's a beautiful prompt structure where I define here the logic that I want to impose on the system. So I define the code in this intelligence shield. What a coincidence that I did this already 2 weeks ago. And then I let O1 or O1 mini in this case run through, so I get here the complete, I see here based on my definitions of the intelligence shield, I can see all the sorts that are enclosed with thinking tags. I have breakdown into smaller steps. I have the step tag. If I have tool use, I can define external actions here for my robotic system. I have here reflection tags where I see where the system tries to go, makes an adjustment, comes back, chooses an alternative route to perform an action. And then we have backtracking in a different approach. So you see, you might notice, hey, this looks already a little bit, yes, it is pure coincidence, my videos. And you might say, but okay, this is just code and prompt. Is there anything else we can do? And I mean, just as an idea, if you want, no? We start here, as in the study by Stanford and OpenAI, here with a simple solution. But we do not take here only GPT system. But now let's say we take here a little bit more advanced code LLM. And what we do, we have now GitHub repos, and we have here from a simple complexity level 1 out of 10. Let's say we have here instead of 4, we have here 10 different code solutions. And then we have a complexity level 2 GitHub repo. And then we have here 10 different GitHub repos with this complexity. And it goes up to a complexity level 8 out of 10, a real heavy code segmentation, code implementation here for particular problems. And our code LLM was trained on all of this. Now, a simple idea is that you don't have O1 as a black box, but you can code your own code LLM, knowing that you have 10 times 8 different code solutions that are working. You verify that these are all working code solutions. And then you say, I make it real simple. I have an idea for the complete data pipelines or data preparation and whatever is your specific task. You just combine different code solutions together. Maybe they have different complexity levels. And then you go to the next step and you combine maybe out of those 10 times 8 GitHub repos with valid code, you combine, you do a permutation and you just look at the performance. You have defined a utility function that is going for an accuracy of the solution. And let's say the first one had a performance of 11 out of 100, and now we reach a performance 25 of 100, and you get the idea. So if you want to make a demo, a simple example, and you want to break up here the hidden secret internal thinking here of all those proprietary AI that will come in the future, you can see even in this simple combinatorial iteration process, we can achieve much better performance if we go to higher complexity level code solutions and we can combine them. And this is in a simple reduced set. You don't need all of GitHub. You just have, I don't know, 100 code segments in your company that you know that are successful in your company. And then if you want to have a self-improving system, you can experiment, you can play. How far can you push here the upward drift in the complexity that a system can solve suddenly if you let it do this self-learning, recursive, iterative process? Now, you might remember I have another video and I was talking about the same kind of process, but now on an agent level. And I showed you we had here this super agent invented just some weeks ago. And the task was also, if I have a code agent, if I have a mathematical agent, if I have a search agent, a common reasoning agent, and I have a multi-agent system. Now, on the level of the agent complexity abstraction level, we had the same problem. If my code agent was a complexity level 4 out of 10 and the math agent had a complexity level 9 out of 10, in this video I showed you here this new super agent. What is the task to allocate your subtask given the complexity performance of our agent? And now if you want, you can do this here on a code base also if you do not have complete agents, but if you have code that works in your company. You see, it is all boiling down more or less to a same architectural idea. We always have to solve here more or less the same abstract logical problem. Now, Stanford tells us here, hey, listen, a fundamental limitation of our published approach is here that the LLM itself is not improved. And told you this at the beginning. So, and they say, since the language model, the GPT-4 model from 2001, themselves are not altered with their data knowledge and their complexity level, Stanford tells us, hey, this is not a fully recursive self-improvement task. And we know this now. And unfortunately, yeah, we might say, hey, why? Why they did this 8 weeks ago and we have not seen now the next step in the evolution here, where they do here the full recursive self-improvement. Well, yeah, we have to wait for the for-profit optimization phase of OpenAI. Or maybe Microsoft, I don't know. So if we would use our own intelligence, you know, this is what we call the human intelligence, there are so many new ideas if you follow this approach. You can think about not only a code generation implementation, but you can think about a task decomposition scaffolding in our intelligence shield. Or you think about an interactive learning scaffolding here if you have multiple agents. Or you think about an optimization of the real-time feedback loops in our intelligence shields. Or you think about the optimization that I already mentioned. If you have multi-agent collaboration with multiple shields, do you put a shield in front of the multi-agent or in front of a swarm of agents? Or do you have a particular protective shield just inside the agent, just in front of your LLM? Or you might ask, hey, or you have the memory in the agent, no? Can we build a memory augmentation AI scaffolding code? Or you say, hey, what about an autonomous experimentation, you know? There's this thing that in science that AI can now conduct experiments here on protein folding, like alpha protein fold 2, that we can use this scaffolding approach here by selecting new set of parameters each time we do here this trial and error. Well, all these beautiful new ideas. Or you go, you say, hey, I'm going crazy. I go now for a multi-modal integration scaffolding here in my shield. So my shield knows how to use multiple AI models. Or you go with autonomous code debugging and optimization scaffolding. You get the idea. This opens up an avenue of new implementations that are, I hope they're gonna be beautiful. So let's see who comes up. Will it be Microsoft? Will it be OpenAI? Will it be Google? Will it be Meta? I don't know, but everything more or less seems to converge to a certain architecture where you have a generic LLM that is so cost effective you don't have to have extra costs for if you're Microsoft or if you're OpenAI, and you can do, or if you want, export all the learning not only for task-specific adapters that we know for 2 years now, but you can do this, if you want the same idea here, for a logic controller that is scaffolding here. All these ideas have the potential to significantly enhance the autonomy and the flexibility of future AI systems across various domains. And I think this is beautiful. Now, for my green grasshoppers, at the end of the video, I always want to do here a little bit of a definition, what I used here. So, definition and core concept of scaffolding. It's like a blueprint or a support structure that guides the AI model through a multi-step process, maybe a multi-step reasoning process, a multi-step code optimization process. And it ensures that AI operates in a logical, manageable, and often recursive way, breaking down large tasks into smaller, tractable components. Why scaffolding is applied? Sorry, there's a typo. There's an explanation for you. Recursive self-improvement is what we are looking for. And a short summary of the methodology for my green grasshoppers. So you see, future direction. And this is now the second reason why now 8 weeks after this was published here, I show it right now. Because now with the publication of Gödels Agent, we have a clear idea where we are heading for. And this is a kind of convergence to future solutions. Because now if also other universities are thinking here about a complete recursive self-improving AI, where we also have the LLM as a self-improving system, I think it is quite clear where we will be heading for. So, future research could explore fully recursive self-improvement systems where both the LLM and the scaffolding problems, my intelligent shields, are refined together. And investigating now open source LLMs. And Microsoft might say, hey, wait a minute, we are just talking here about our OpenAI systems. You want to open source this? Yes. Because if you have an open source LLM and you can do the fine-tuning yourself, and you don't have to pay a crazy amount of money to OpenAI or Microsoft, this will enable self-improvement across a range of applications. And this, I think, is another very promising area for the future development of AI. But more about this in my future videos. I hope you enjoyed it. I hope you found some new ideas. And it would be so great to see you in my next videos.